Hi, in this video we're going to be doing a quick review on acids. Now first let's talk about strong acids. Strong acids ionize completely in water, 100% in water. And so when we want to find the pH of a strong acid, all we have to do is find the molar and take the negative pH of that, and that is the concentration of our H2O+. So for example, if we want to find the pH of, let's say, 3.0 times 10 to the negative fourth power molar of a strong acid of HCl. Again, strong acids are HCl, HBr, HI, H2SO4, HNO3, and HClO4. These are our 6 strong acids that we'll be using. Now, HCl is a strong acid, so when we want to find the pH of that, HCl plus water, HCl will donate its proton to make Cl minus, and sorry, this is not double arrow, this is a single arrow because HCl is strong, plus H plus H3O plus. Now since 100% of this 3.0 times 10 to the negative fourth molar will ionize, that means this number will be the same as the after concentration, right? Minus X, and this is plus X. Since this will end up being 0, so this starts off with 0, so this X, and since this side is minus X and this side is plus X, this number will be equal to this number. Now this number, we start off with 3.0 times 10 to the negative fourth minus 3.0 times 10 to the negative fourth equals 0. So over here plus X, this will be plus 3.0 times 10 to the negative fourth. So our concentration will be 3.0 times 10 to the negative fourth. And our calculation will be pH is equal to the negative log of the concentration of H3O plus. So all we do is have to take the negative log of this, 3.0 e to the negative fourth, and we'll get a pH of 3.52. And that's it. So basically just use the concentration that you're given with, taking the negative pH of that, and that is taking the negative log of that, and that is your pH. Now weak acids do not ionize completely in water, so that's when we need to start using Ka in the equilibrium equation. So for example, we find the pH of 2.8 molar solution of HOCl. Now we first need to write an equation, HOCl plus H2O. What will happen? Acid will donate its proton to the base, and since this is a weak acid, it's going to be an equilibrium with double arrows. This will form H3O plus and OCl minus. Now we can use 2.8 molar over here, minus X, 2.8 minus X. We don't care about water. This will be 0 and 0, and this will be plus X, maybe 2.8. Nope, sorry. It's going to be X over here and X over here. Now, what is the Ka for HOCl? Well, if an acid in the reactant, we'll just use the Ka of the acid. Now, the Ka of the acid should be given. This time we're given that Ka is equal to 3.47 times 10 to the negative 8. So what we do is, since 10 times 10 to the negative 8 is a really small X number, so 2.8 minus X practically means nothing. It makes no change at all. So we can cross out the minus X over here, and this will mean X squared divided by 2.8 minus X. Again, when the X is extremely small, you can cross out the plus or minus X's. Now that you're in this equation, you can do, oh, sorry, the minus X is gone on the bottom. You can do 3.47 e to the negative 8th times 2.8, and take the square root of that to get you X is equal to 3.12 times 10 to the negative 4. And X is the concentration of H3O plus. You can use the concentration of H3O plus to find the pH. So pH is equal to the negative log of X, which is 3.51. And if we're dealing with percent ionization, just remember to use your given pH and multiply it by the ionization, and that will be the change. That will be your X value. So let's say the same question, 2.8. If it tells you that 0.52% ionizes, you'll divide this by 100 first to get the to get the actual value, you set a percentage. So let's divide by 100 is 0.0052. So if 2.8 molar of HOCl and 0.52% ionizes, you're going to use 2.8 times 0.0052. And it gives you a number of 0.01456. And that is how much molar of HOCl will ionize. So you're going to use this number and plug into X to get a new equilibrium solution. And since this X over here is going to be the same X over here, you can use this number and just find the negative log of that to find the pH. Right, now let's quickly talk about polyprotic acids. Polyprotic acids are acids that have multiple protons that can be donated, like H3O plus, H3PO4. And then we have H2PO4 minus, and then we have HPO4 2 minus. And this will go like this: H3O plus, H3PO4 plus first adds water to form H2PO4 minus plus H3O plus. And then this plus H2O will form HPO4 2 minus plus H3O plus. And finally this plus H2O will form PO4 3 minus plus H3O plus. And this will be K1. For this equation, we're going to use K1. For this, we're going to use K2. And for this, we're going to use K3. And when do you know which one it is? Look at the products and reactants. If what you're dealing with includes H3PO4 and H2PO4, then you'll be using K1. If your reaction has H2PO4 and HPO4 2 minus, then you'll be using K2. If your reaction has HPO4 2 minus and a PO4 3 minus, that is when you're going to use Ka3. And Ka, all these K are given: K1, Ka2, Ka3. K1 is 7.5 times 10 to the negative third power. K2 is 6.2 times 10 to the negative 8th power. And K3 is 4.8 times 10 to the negative 13th power. Notice how K1 is significantly larger than K2 and K3. That is going to be the case in most situations. The K1 value is usually much greater than the remaining ionization values, because the H plus from the first ionization causes the remaining ionizations to shift left and favor the reverse reaction. Therefore, in general, when we're calculating the pH, we're going to use the concentration of H plus in Ka1 only, because the other two are way too small. So, for example, what is the pH of a 5.8 molar of H3PO4? So in that case, we're going to use H3PO4. H3PO4 plus H2O forms H2PO4 minus plus H3O plus. Look at products reactants. We have H2PO4 and H3PO4. H3PO4. We have H2PO4 minus and H3PO4, and only that corresponds with K1. So we're going to be using K1, and we're told we're 5.8 molar. So we're going to use the rice chart. 8.8 minus X is going to be 5.8 minus X. This is going to be, we're going to cross this out. This is going to be 0. They start off with 0 plus X, and it's going to be 5. This is going to be X. Let's take a look at K. Our K is 7.5 times 10 to the negative third. That is not a small number. So this time we're going to need to include the plus or minus X. So we're going to use Ka is equal to the products, which is H2PO4 minus, times the concentration of H3O plus, divided by our aqueous concentrations in our reactants, which is only H3PO4, because H2O is the water. Now this will equal X squared divided by 5.8 minus X. And we do not delete the minus X again because our Ka value is big. And to do this, we're going to use K1 over here. K1 is 7.5 times 10 to the negative third. So we're going to go to a graph and go to 7.5 times, actually no, we're going to plug in the fraction first. X squared on top and 5.8 minus X on the bottom. Subtract by 7.5 e to the negative third. And then we're going to go to our graph to solve for pH. Okay, the X value is 0.205, and that is when the line crosses the x-axis on the right. So now, what does the X value tell us? X is H3O, the concentration of H3O plus at equilibrium. Now we have the concentration of H3O plus. We can do pH. pH is equal to the negative log of 0.205, and that is going to be negative log of 0.205, which is 0.69. So that's our pH. Our pH for this acid is going to be 0.69. Something else about acids is that some cations can acidify solutions. And when you think about lattice energy, a metal ion with a larger charge will have a stronger attraction for the electron density from the oxygen atoms in water, which makes them a stronger acid. So higher the charge equals stronger acids. Now, if two charges of the different metal cations are the same, then we look at the radius. And a smaller ionic radius leads to smaller intermolecular distance to oxygen. And since the distance is smaller, that means it's going to be have an increase in acidic properties. And finally, group 1A and group 2A cations, so our metals in group 1 and 2 will have very large radii or small net charge, and therefore will not affect pH. Another explanation is that they're going to be weak conjugate acids of strong bases, like KCl, right? KCl, K is in group 1, so this K will not be affecting the pH because it's conjugate. It's going to be a weak conjugate acid of a strong base. And this is our review on acids. Thank you for watching.